Okay, perfect. So, okay, hi everybody. We're happy today to have Michael Toomey from Brown University, who is going to speak about deep learning in the dark sector. So, please, Michael.
Great, thank you so much. As you said, my name is Michael Toomey. I'm from Brown. I'm a student of Professor Stefan Alexander, and I'm going to be talking about some of the work we've been doing over about the last 4 years or so on applying machine learning methods to trying to sort of dive deeper into the dark sector. So without further so I just first want to flash up the large group of collaborators we have. So we have a mixture of machine learning experts, experts in cosmology, some people in particle physics, a bunch of grad students, undergrads, even some high school students working on the project. And so far to date, we've come up with a bunch of really interesting, awesome papers that I'll sort of dive a bit into as I go through the talk. So I won't spend too much time there, but sort of what's the point of what we're doing with this entire, this entire program is, where's the dark matter? If all attempts at trying to find its interactions with a standard model have come up empty, right? But one way that we do know that dark matter, we can understand it quite clearly is how we discover it is through its gravitational interactions. And sort of the premise of what I'll be getting into is ways in which we can use a specific way of looking at dark matter substructure, specifically as a probe of classifying and understanding different models of dark matter. And then I'll get into about how machine learning plays a role in this as well. So there's a few popular ways, these aren't all of them, but a few ways that you can actually go into saying something about dark matter substructure. And so that one of them is stellar streams. There's astrometric coulometry, which is looking at induced velocities and accelerations and some background light source. So that could be quasars, that could be stars. And another way, of course, is probably the most obvious, is looking at gravitational lensing. So specifically what I'll be talking about today is this in the context of strong galaxy strong lensing. I'm just highlighting. So I did talk about this a bit earlier at I think it was the Astro Coffee or whatever, a bit about this work that I did with Savas Kushiapis on astrometric coulometry. But now into strong lensing and substructure. So it turns out that, so as I said, substructure is a very important piece of information about actually constraining different models of dark matter. And one of the best ways to do this is with strong lensing, because the extended lensing arcs are actually incredibly sensitive to substructure. And so actually substructure has already been shown to exist, not to the point where you can actually start to constrain dark matter models, but people have been able to calculate or put limits on actually what fraction of mass should be in substructure. And it's about order 1%. So people have done this with ALMA, people have done this with like extended galaxy lensing arcs. And so that's basically the basic picture. But one of the major problems with actually trying to go out and understand substructure with strong lensing is that really there's not a lot of good data. And a lot of the data that is around, the quality isn't exactly great. So, best case scenario, you're looking at maybe 1,000 galaxies that are strongly lensed that maybe you could look at and try to constrain dark matter. But the bright side is you have future experiments coming online, like Euclid and VRO, that should be increasing the amount of strong lensing images we have, into the order tens of thousands. And of course, that's actually starting to get into the regime where actually you can start to do some interesting data analysis. But in this work, obviously, since we don't have this information, what we're doing is we're just looking in the controlled setting of simulations for this work, to sort of do proof of principles about extracting this information. So of course, one could say, you could just naively implement some sort of Bayesian model for modeling your substructure and do that. And of course, people have done this. But one of the problems is this is like incredibly expensive to do. It can sometimes take days to extract this information. And so it's, it can be prohibitively expensive to do this. So sort of the premise of what we've been doing in this entire thing in our line of work is actually looking at machine learning as an alternative method to actually get at the substructure. Since you have to pay the price of computation on the training side, but on the, when it comes to actually analyzing something once you have it trained, it's almost instantaneous. And so now I just want to outline our entire program. So this is something that was recently funded by the NSF. And so the basic premise is our SLINGSHOT program. So that's strong lensing inference and generative system for harnessing observational telescope data. Is basically the idea is we're starting off by looking in this controlled regime of simulations, but doing something that's unique from what other people haven't considered is looking at what the dark matter substructure signal should look like in strong lensing images for different models of dark matter. And then taking those simulations and then doing all kinds of proof of principle machine learning applications on them. So that includes doing anomaly detection, basic classification, and then also regression. And then our ultimate hope is to actually be able to then transfer some of this knowledge over into real data using various methods such as domain adaptation, which we'll get into a bit later. But also we have some aspirations to even look at real data. This isn't something we've gotten into, that's why it's sort of in the red panel off to the right. Also potentially trying to extract information from real data itself. So that's sort of the outline. And I just sort of want to work my way through a few of the various boxes on the left-hand side. So at first order, the most important thing that we've been considering, as I mentioned, is actually thinking about different models of dark matter and the effect that that would have on substructure. So to date, we've included and developed a bunch of different simulations for different models of dark matter. So we have a no substructure case, which will make sense in a bit. At first, that doesn't really make much sense, but you'll see why in a minute. We consider just your standard cold dark matter with NFW type subhalos. We've also included ultralight dark matter simulations, and we've also considered ultralight dark matter simulations with vortex substructure. And this kind of is also degenerate with like superfluid models of dark matter. And we're also currently working on including self-interacting dark matter models and also BCS dark matter. And this probably isn't exclusive. We'll probably end up adding more things to this, but this is sort of our wish list for now. And I just want to make a quick note on the vortex substructure because I suspect this is something a lot of people aren't familiar with. So basically, vortices are a solution that you can get out of the Gross-Kravitsky equation, which is basically just the equation of motion for your BEC dark matter. And you can just qualitatively think of it as like a non-relativistic cosmic string, right? So the cosmic string is the solution to a Klein-Gordon equation, whereas the vortex in this case is from a non-relativistic limit, so it's just the solution to a Schrödinger equation. So you can just sort of map your intuition for a cosmic string just onto a vortex, just thinking that it's some non-relativistic limit. And here's a really cool image that I simulated of what the lensing looks like on a background galaxy if you have a vortex. And it's actually quite cool because there's really not much magnification, but you get this interesting image splitting because it actually cuts out some what's called the deficit angle from the lensing. So now we have this pipeline of all these different dark matter models that we have with all this knowledge. Now what we want to do is we actually want to do the simulations. So what we do is we actually start off with an image of a real galaxy. And this is actually critically important because you need to marginalize over the various structure that's in background galaxy itself if you actually want to say something interesting about real substructure, right? Because you can imagine if there's structure in the background galaxy that's being lensed itself, that could be misconstrued potentially if I just naively apply this to real data from simulations with substructure, when in fact it's just structure of the background galaxy itself. So we then take these real galaxies, we rescale them to correspond to, we like to take galaxies that are a relatively close redshift to avoid too much contamination in background. We also filter them with a Gaussian to eliminate excess background noise, but we resize them. We then include our dark matter model, so whether that be some sort of cold dark matter model or that be our vortex type substructure, whatever it be. You can then also, on top of that, we also critically include interlopers. And interlopers are just dark matter halos that are in between us and the galaxy, or the dark matter halo that's of interest to us. It actually turns out that when the fraction of mass in substructure is less than about 1%, this actually dominates the signal when you look at strong lensing. So actually interlopers are critically important in calculating these lensing signals. So you can't ignore them. So we include those.
How do you put them in? Do you have a long simulation or is just by some?
Yeah, so this is, you just do like multi-plane lensing and then you just populate them with like a Seth Torman type mass distribution function. And then, so once you have your dark matter model, you then go ahead and you actually go lens that. So this is like a perfect lensing, so there's no noise or anything in this image. And then you can specify that to whatever instrument you want. So whether that be a Hubble type instrument, whether that be Euclid, whether that be an ALMA observation. I say ALMA, you need to be careful about, because that's interferometry, but you also have to account for like PSF and all the various effects of the actual instrument. And then from that, you then get your final lensed image that's some proxy for some observation. And that constitutes our training set with all the different dark matter models that I just discussed. And I just want to flash up a couple examples of what these might look like. And to be clear, these aren't the same galaxy with different substructure, they are a different substructure, but they're also different galaxies with different lensing configurations. So you shouldn't see, oh, this is a drastic difference between cold dark matter and axion. I'm just showing a few examples of what the data set might look like. And the point is, naively by eye, you can't really tell which one is which. And here's like a toy model, right? So what's actually the signature that you're going after? In this case, I don't have any interlopers. This is just a basic lensing thing. So this isn't even like a realistic distribution of like subhalos on the right anyway. They're just to give people like an intuition for what the signature might look like. So these are residual maps. So basically what I've done here is I've just taken a dark matter halo with no substructure, lens that, taken another dark matter halo with like just a line defect, a few subhalo type things plotted down, and just take the residual of those two lensing images just to give people a flavor for sort of what is this machine learning algorithm actually going after. And it's that you distort where some of the light is, in the image, right? There's some distortion, which is perfectly intuitive.
So
and
what's the background? It's a quasar or what is the background?
oh, the background is a galaxy.
Another
So there's some background galaxy. And this is, and as I said, this specific thing I'm showing is very much a toy. We don't actually use this particular, because obviously there's not enough subhalos on the right hand side. It's just like a visual aid. But yeah, this is simulated with like a Cirsic light profile on the background, not even a real galaxy, but it's a proxy for a galaxy. Exactly. But the point is there's a very distinct difference in the morphology of a vortex type substructure versus cold dark matter. Obviously, looking at like ultralight dark matter with cored subhalos, there's going to be a bit of a degeneracy between that and NFW substructure, of course, because, you know, they're kind of similar, but of course they're also different. So now getting into the machine learning. So I sort of described how we made our simulations and how those work. I guess just stop and ask, does anyone have questions about the simulation side of things? Okay, I'll assume not. So now moving into the machine learning thing. The first order thing we want to do is actually do something called anomaly detection. And the point of doing anomaly detection is basically we want to make sure that we actually have sufficient information in the lensing arcs to actually then pass it on to other machine learning information or other machine learning algorithms. So you can imagine just by random chance that, because remember the most information is in the lensing arc itself. So you can imagine just by chance that I have subhalos that are just not near the lensing arc, right? So that actually doesn't contain enough information for us to say anything about substructure at all. So the first order machine learning goal is we need to find lenses that have substructure near the lensing arc.
Sorry, okay. What are we seeing in the right?
Oh, this is
what is the?
Yeah, so this is another residual image. So I should make this clear. So this is just another, it's the same image as before. Maybe this isn't the best image to show, but it's just another residual image. And you can see where the arc is right here in the bottom. Right.
Yeah,
so,
but yeah, I just wonder why there is a residual. The residual of what, sorry?
It's the model with no substructure minus the model with substructure.
But of what? Of the light?
Of the lensed galaxy.
And why is there light? I thought most of it was just in the arc. So there's
it is because so it's a normalized residual image. So basically it's showing the fractional, that image is showing the fractional change in light.
So in the center, really, you're showing something, but there's nothing there really.
Yeah, exactly. So yeah, it's probably, I probably need a better figure for this, but what, you know, qualitatively, right, there's like maybe an order 4 or 5% change in the light, but the most light is on the bottom where the lensing arc is, right? So actually like this, like what I'm showing here is on the upper with the green circle is showing you a subhalo that does have about an order 4 or 5% change in the light, but because it's nowhere near the lensing arc, it has no light. So it really doesn't mean anything at all. Versus this particular subhalo that's right on the lensing arc, it's also a 4 or 5% difference, but it's right on where the light is. So actually that makes a noticeable difference. And so the idea is to then use something like an autoencoder that will then identify that. So I guess just to start off by saying what an autoencoder is. So basically, this is the mechanism that we'll use to actually train this anomaly detection algorithm. And the way this works is we just take, say, one class of images. So this is our no substructure class. And we train this architecture just to learn basically what a lensing image looks like for whatever experiment we want with no substructure incredibly well. And that's just a proxy for having no subhalos at all near the lensing arcs, right? Since that's the most important information. And then what'll happen is, so if I pass it through, it's going to try to reconstruct that image that I put in. But if I put through an image with a different type of substructure, say I now put through the simulations are all exactly the same, except now I've added in substructure. What'll happen is you'll then find areas where the loss, the difference in that image that's put in and output by the neural network is on average higher. So that extra loss, you can say, oh, okay, that's a subhalo, right? And the way that you quantify that, and indeed for that particular image that I passed through, there was a subhalo there. And you can make that a little bit more quantitative by plotting the distribution of losses. So I can take that two-dimensional image and I can just compress it down to one scalar value. And that's the reconstruction loss of that image. And then I can just plot that distribution and I can decide on some threshold And I can say anything above this threshold corresponds to an image that has substructure. So then those images can then be passed on to the rest of my machine learning pipeline, because images that are below that threshold clearly don't have sufficient power or sufficient perturbation in the lensing arc itself to actually have any information. So we don't want to pass it on to something to go make a decision that we're going to make a claim about if there's actually no information there to begin with.
So is this a distribution of these percent residuals, or is already scaled also by the amount of light that's coming in?
So this is the input image and the output image at the autoencoder, because the autoencoder is reconstructing the image that was given. It's taking the difference, and then you're basically summing up that difference to one scalar value.
Everywhere.
Right. And then you do this for your entire data set, and then you just histogram it. And that's what this is showing for the two different classes. So blue is with no substructure, and then red is with substructure.
But why would this be the best thing to do? Because I assume that in practical purposes, most of the time there's no substructure. Sometimes there's one or something. So there's like a handful of pixels in the image that are off, right? And we're near the, and now you're adding over the entire thing. So are you not diluting yourself by?
No, I don't think so. So you mean in terms of reconstructing the final loss value?
Yeah, to decide that, oh, there's something off. If your statistic looks at the sum of these residuals everywhere, as opposed to knowing that only a small fraction of it will have a big thing whenever there is a substructure, and most of them are junk. Like there's nothing there. So why would I sum everybody as opposed to looking at see if there is a very high thing or something like that?
I mean, I guess that's something. So you're saying just like looking at the residual, or sorry, the difference of the two images, right? The reconstructed and the original, and just saying if the value is above
something.
Yeah, I think you could do that. This is a pretty standard practice for doing anomaly detection, so that's sort of why we're doing it.
But maybe this was
I think
came up with it in some situation where there's more, widespread anomalies, like as opposed to like a one spot. I don't know.
No, that's a good point, right? And we've also looked at the anomaly maps themselves, because actually sometimes they have information about the substructure. At the end, I can show you a cool image that basically you can actually make out a vortex, because you can basically see, right, it was the architecture is trained on no substructure, and then we pass through vortex substructure, and you find that if you look at the error in the map, you can actually see the imprint of the vortex itself. So it's kind of potentially a way to, like, in an unsupervised model agnostic way, potentially identify and say something about substructure, potentially. But yeah, I think what you said you could do in principle. We're just sort of following normal conventions in machine learning here. But no, great question.
Can I also ask a question?
Yep.
Hello, Michael. I'm Peter. I'm trying to understand why you run anomaly detection before everything else. And the reason I'm asking is, I'm guessing that you try to find or try to identify and classify whether a set of images fundamentally tell you something about whether we are in a CDF or some CDM or more complicated dark matter scenario. So you basically try to distinguish whether reality eventually prefers one model over the other. If you run anomaly detection first, then you basically identify maybe the most prominent things, but that doesn't mean that it's overall that the data set that you aggregate actually has more information. You're throwing things out that this anomaly detector things isn't relevant enough, but the subsequent analysis might actually exploit. So I wonder why you think you need to run the anomaly detection at the beginning.
Right. So I see what you're saying, that if looking at the combined data set together instead of just on an image by image basis. And yeah, so this is something we've thought about doing, and it's probably something we'll end up actually doing, is not doing it this way, because I think we sort of came to that realization afterwards that maybe this wasn't the best way to do it. But it is a way if you just want to go on an image by image basis, because obviously in the real world, it wouldn't make sense to look at a bunch of different lensing galaxies, right, and say, oh, this one's got cold dark matter, axion dark matter. Actually, you could just collectively look at all of them and then inference from that. But no, I understand what you're saying, and that's a good point.
Yeah, actually, even in the real world, or actually, I would say, especially in the real world, you probably don't want to make strong decisions up front, because a lot of stuff will look a little bit weird, a little bit wonky, and not quite as clear as you have it in the simulation. So I think that task here, anomaly detection, is notoriously difficult. And if you inject some instrumental noises many of the things will look like anomalies, although they are not. And so you might end up with a data set that is incredibly small of something that is obviously something highly perturbed and detectable. And so you end up throwing away much more than you probably want to.
No, of course, right, yeah. And so, yeah, no, I don't disagree with you on that. No, good point. Okay, and then so just moving on, you can convert these distribution of losses into a nice ROC curve by just changing your various thresholds. And you can just quickly by eye, you can see actually these algorithms perform quite well, but again with the caveat, this so basically, so sort of in our pipeline, a modulo maybe differences with using this anomaly detection algorithm. You can then imagine taking that data that have now passed through that initial anomaly detection step onto a straight up classifier. And basically, it's just the idea, again, just straight up classification. Is it this dark matter model or that one or this one, right? And then, it's pretty easy to do. And it turns out, so we tried using both ResNet and AlexNet. And so that's our dashed lines up here. Now this is a little laggy, I guess. But you can see that it's almost a nearly perfect classifier. So it has AUC scores near 1. And then, so that's a really quick step, but that's with the goal, of course, of then moving on to a regression algorithm, right? Because it makes no sense to apply a regression algorithm to some other type of dark matter. So that's the point of having this initial classification step. And so this is something that we're very actively working on. So I can only show some preliminary results. But I think this is a really cool plot showing we're basically what we've done here is we've actually looked at, and we're doing this for the other dark matter models as well for various different parameters. But what I think is really interesting is you can actually regress on the mass of the axion directly in the vortex mass case, and also as well as for the regular chord substructure for ultralight dark matter. You can also do that as well, and that's work in progress. But here's a nice plot showing some initial results for extracting the axion mass. And this is just where a proxy for the mass is approximately the Fourier wavelength of the vortex. And that'll correspond to the axion mass. So that's just some interesting results. Can't really say too much on that because again, it's work in progress, but I thought I'd flash that.
So this is each point corresponds to what?
Oh, right. So sorry. The left-hand side corresponds to, I believe that's the left-hand side is the predicted, or the y-axis is the predicted value from the neural network from our regression algorithm of the axion mass, and also for the fraction substructure on the left-hand side. And then the x-axis corresponds to the actual true mass from simulations.
And there's 1 point for each one. Lens,
There's, for each lens, that's correct.
and why are there 2 panels?
So yeah, sorry, I guess I'm too excited about the axion mass one. So the one on the left is the fraction of mass and substructure.
And the other one is the
Axion mass.
axion mass. So how is it possible that on the basis of, should I interpret this that on the basis of the one example, you can tell the axion mass, pretty good just in an individual for
So
each of them? Like, I don't know, this catalyst look like 10%. I don't know what
it's actually not a
factor of 2 or something.
Right, so it's not too crazy because this, I don't think I mentioned before, our axion vortex is a bit of a toy model, right? Because axion vortices aren't well understood. So we're using a bit of a toy model there. So basically, it's basically probably learning the length of the vortex. And that's not too hard for it to understand, right? Because you can think of, I have a vortex spanning the image and I have some lensing arc. All it needs to basically do is have some distortion of the lens over here and the distortion of the lens over here, and it can kind of interpolate some distance from that. And that's most likely what it's doing. I don't know if that makes sense.
So you're saying that in this model, there's not just one subhalo somewhere, but it's like a full arc screwed up in a very strange way.
Yeah, so you would expect, so we're looking in the very, light axion mass range, like 10 to the minus 23. And you expect about 1 vortex per de Broglie volume. And given the size of the image we're looking at, it's about 1 de Broglie volume. So you would only expect maybe 1 to 2 vortices, maybe, in any lensing image, looking at this particular mass scale. Now, as you start to bring the masses up higher, like 10 to the minus 20, first of all, you're not going to be able to see the vortices anymore because they're going to be like inside the solitonic core, which at that point is actually quite small. And you probably wouldn't be, it's like probably parsec scale at 10 to the minus 20. So you could not resolve that over cosmological distances. And in that case, that's where we actually, instead of looking at vortices, looking at the distribution and population of subhalos instead. Right, because the distribution function for axionic dark matter looks different than like cold dark matter. So that's sort of the signal we're going after for those higher mass axions.
Yeah, I'm just confused by the fact that if I were thinking of CDM and I saw something in the I would be it probably would be a hard time even to tell the mass of the substructure thing, because you don't know how far away from the arc is, and probably it's a huge degeneracy of parameters.
Do you mean the axion mass, or do you mean
the mass of the substructure? I was just thinking.
Oh, you mean the mass fraction?
No. Just that was the okay. Anyway, maybe we discuss it.
Okay.
I'm thinking.
Right. Okay. So now sort of the last piece of sort of what we've done in this program is starting to consider sort of in advance how we actually might go from our algorithms that are trained on simulated data to then move them over into real data. And so the question is, what happens generically if I take some model trained on one data set, say it's simulations, and then try to apply it to real data? In general, it's not a good idea, right? So here's an example where I'm showing the ROC curve for an algorithm that was trained. So there's a source and a target data set. So source is in black, the target data set is in blue. So basically what we've done here is we've trained a neural network on, I think what we did here was HST type simulation. And basically we trained it to do classification. But you could of course do this for regression or anything else. And then we naively applied that to a Euclid type simulation. Again, just as a proxy to see what happens when you're changing domains. And what you can see is that the blue curve is significantly degraded relative to the black curve. And that's because of this difference in domain. The domain is different, right? The parameters and the background and the noise and the point spread function and all of that information in a Euclid type simulation is drastically different from HST, and that throws the algorithm off quite a bit. I guess I just said in words what these arrows are doing. So let's get through that. So one way to account for this is using something called domain adaptation. And the basic premise of domain adaptation is that I initially sort of train on this source data set, like I explained before. So let's say we train a classifier between different types of dark matter on a HST type experiment. And then what I want to do is I now want to transfer that information to then do classification on the Euclid experiment. Or you could also imagine train on simulations and then transfer this over to real data. That's another example. And here's schematically what's going on. So basically one way to do this is using unsupervised domain adaptation. So in the context of the real world, we don't have the privilege of having necessarily any information about what's going on, right? Because that's the real world. But in the context of simulations, of course, we know what the labels are. We know everything from our simulations. And so the first step in doing unsupervised domain adaptation is you first, and in this example, I'm talking about a classifier, but again, you could generalize this to regression or whatever type of machine learning problem you want. It generalizes to whatever. What you do is, in this example, just train a supervised classifier to classify between different types of dark matter models. What you can then do is you can then enter this into an adversarial adaptation environment. So basically what you do is you take this piece that the CNN bit, you basically cut off the classifier portion of your initially trained architecture, and then stitch it into this adversarial adaptation architecture. And basically what you then additionally do is you now bring in another basically encoder. So it's basically taking, say, what we now want to do is, I guess it's the other way, but let's say it's real data that we actually want our architecture to actually classify. We then bring that architecture in. And basically the goal of what's going on here is we want to go into basically a latent space. And we want to trick the algorithm into not being able to distinguish between my simulations going through the encoder in the top or my real data going through the encoder in the bottom. So basically, this adversarial adaptation works to try to get those two projections in a latent space to overlap each other. So that's, if anyone's familiar with like generative adversarial networks, it's very much the same idea. And so basically, your hope is that if I put an image through with one type of substructure, no matter what simulation it is, it'll be projected into the same place in this latent space. And I guess this is, again, a schematic of sort of what I was just saying. And then once you've done that, you can actually then take off this piece from your adversarial adaptation step, and then you can then grab the classifier from your originally trained supervised classifier because you've learned the same encoding for the same classification problem. So you can just stitch those two together, and now you have your new target classifier, which has now been domain adapted to basically do the same problem, but in a different domain. Domain here meaning, in this context, different instrument, different points per function, real data, simulated data, for example.
Is this faster than just training it again? That's the thing.
Well, so the problem is, right, so if I wanted to apply this to real data, and let's say I wanted to do classification for something, obviously in the context of classifying dark matter, that doesn't make much sense because there's only one dark matter. But let's say we were doing something like, I don't know, counting how many subhalos there were or something like that, right? In the real world, we don't know what that is, but in simulations, we do. And so because this is an unsupervised domain adaptation, I don't need information about what the real true label is through this process that I was just describing. So you can adapt it as long as you're trying to go after the same type of problem, right? As long as the domain is the same type of problem, right? In this case, you know, this toy example.
And I think that you're using as the truth, the train, the first one.
Right.
The first one.
And then the adversarial adaptation step basically just learns to, this is what this picture is kind of showing, is that if you just naively before training put, say the left-hand side is your initial trained data set. This is like your latent space. And then the right-hand side is, say, the real images that you're putting through. Basically, the goal of the adversarial adaptation is to get those two distributions to overlap with each other. So it basically learns, you know, if I put through an image in this context that has like some type of substructure, it learns which one to map to in the latent space between like the two different encoders. Does that make sense?
Yeah.
Okay. Let's see, was there anything else there? And then, so you can sort of understand how this works by looking at, again, rock curves. So it's the same plot as before with the black and the blue lines, but then these, I guess, cyan, red, and purple lines are showing you what happens with various different domain adaptation algorithms. So I was just outlining adversarial domain adaptation. So that's the purple line. The reason why I went through that one is that was our best performer. But you can see that it drastically improves the performance of applying our architecture. It was originally trained on one set of simulations to another through this domain adaptation process. So it goes from like an AUC of about 0.85, which isn't too good. That's probably like an accuracy of about 70–75%. If you want to think in terms of accuracy, up to an AUC of about 0.98, which is, you know, pretty close to being a perfect classifier. And so that's, I guess, the conclusion of the talk. So basically, just to conclude, dark matter substructure is the very important and viable method to potentially distinguish between different models of dark matter. Strong lensing in particular is incredibly important and a very sensitive probe of that substructure. And machine learning techniques should turn out to be actually very important in this endeavor of trying to potentially, extract information about what dark matter is, distinguish between them, regress on different information, whether it be, the mass of the axion or something or whatever, because it has more flexibility than like a traditional Bayesian approach. And also, of course, with the expectation that there could be potentially upwards of potentially 100,000 strong lensing images, doing traditional Bayesian methods on those seems computationally intractable potentially. And then also there's the benefit that you may be able to transfer knowledge learned in a simulation setting into the real world with domain adaptation techniques. And I guess with that, I'll conclude.